speaker will be Aooorv lngle from the University of Kansas, who's going to talk about bunch separation polymorphism. Aooorv.
OK. Cool. So this is ongoing work with my current advisor, Garrett. So please ask simple questions to me and difficult questions to him. OK. So linear types are great. And linear type systems have been used in programming languages to model resources. And recently, they have been used in languages like Rust, Clean, Linear ML, and also Haskell. And they're good because they give guarantees about memory safety. They're also good because they prove or they give guarantees of session fidelity in communicating channels. So the reason why linear types work is because of the controlled use of contraction and weakening, which are just fancy terms saying that you can duplicate stuff and you cannot drop the stuff from your context. So this gives a semantic interpretation of consumption, where it says that or consumption where it says that, well, you count the number of times you use a resource in your program or in the function. So, so this also gives two kinds of pairs in the language. One is the multiplicative pair, where you have to use both components of the pair, and the additive pair, where you use only one component of the pair. So let's try programming in a linear language and try writing a swap function on both the kinds of pairs. So in multiplicative pair, you would expect a simple thing where you take the components apart, swap them around, and everything is fine. But when I try to write a swapping function on an additive pair, we see that there is some sort of an awkward asymmetry. What I wanted to do is write a swapping function on a pair. And I would expect that a same term should be able to do that. But that's not the case with linear logic. So let's take a step back and try to change the meaning of what we mean by resources. Instead of talking about, instead of having a notion of counting the number of times you use an argument in your function, let's think of them in a sharing or separation way. And there's a logic called logic of bunch implications that does that for us. So in logic of bunch implications, we would have two kinds of pairs again. The multiplicative pair would be for a pair that is separate, which means that the resources are separate, and that's denoted by a hash there on the first line of the code. And in the second line, we would have the additive pair, which is nothing but the pair is shared, or the components of the underlying represented resources are shared. So now if you squint hard enough, we see that we can kind of erase both of these or parameterize both the sharing and separation at type level and come up with a system that is like BI or BISC and say that, OK, now we get a swapping function that works on both kinds of pairs, the additive pair and the multiplicative pair, which is what we wanted. Now we can do better by erasing the types of the terms, because we also have type inference in BISC. So what's the current stage? In bunch implications, we have contexts that are trees, because we would have to enrich the information of whether resources are shared or separate into the context. And this kind of gets tricky when we talk about type inference. So what we do is we represent trees as graphs, where each node would represent the resource, and the edge between them would represent whether they are shared or separate. We also have an implicit polymorphic calculus and an explicit calculus, which would and an elaboration process, so that the user would just write the implicit calculus, and the elaboration would take care of adding all the type annotations to the term. So we have type checking or type inference. So we don't need an evaluator, right? Because if it type checks, then it works. Why do we evaluate the term? But we are still working on operational semantics, which is aware of the separation or sharing between resources. There are two kinds of extensions to this work. One is adding the explicit drop in the term language. It kind of complicates. It's kind of tricky because the position of the drop determines what the type or the most general type will be, which is a little tricky in type inference. And currently we have only have resources that are either completely shared or are separate. But in real world examples, we would have resources that are partially shared. So we would want to extend the language that would have partial sharing, where in this case, if we say that, okay, the resources in T, all the resources in U are already in T, then we can implicitly drop U, and it should work still fine because we are not discarding any resources. So in summary, linear types are good. Logic of bunch implications has been used in programming logics, but they still have to be explored in the area of type systems. Thank you.
We have time for a couple questions. So one thing that we've seen in some deployed substructural type systems is that linearity is not always required, and affine type systems seem reasonable. Is there a reason that you've decided to go with linearity as what you think of as important here?
Well, yes, but I need to come up with a good reason for it, right?
So session fidelity in particular depends on linearity, because there the point is that the type of a channel is a contract on its usage, and so discarding a channel, as you'd be able to do in an affine system, would amount to not finishing that contract. So I think of linearity as having maybe a few more examples. The story is the same for affine. Okay. Thank you very much.
Is that fine? Okay. Okay. Hello.